Welcome back to Elements of Chemistry tutorials. We're still in chapter 7 talking about the periodic table, and today we're going to talk about the landscape of the table. What makes up the actual periodic table? First of all, it's a table of squares. The squares represent elements, and each element has a symbol that is one capital letter, and then if we need it, a second letter that has to be lowercase. So you've got to be really careful that you don't write in all caps because it would be wrong. Okay, not all the names are in English. Some of them seem a little weird. Oxygen comes from the Latin oxys and gens, which means acid forming. Helium comes from helios, the sun. Helium was first discovered by looking at spectral lines from the sun. Sodium comes from Na, from natrium, salt. Gold comes from the Latin for gold. Oh, it says golf, but it should be gold. Typo here. Arium. Okay, so some of these are really easy to mix up. Students I've found over my vast experience want to say S instead of Na for sodium. S is sulfur. Okay, K and P get mixed up. K is potassium and P is phosphorus. It used to be we could always say there's no FL on the periodic table, just F for fluorine. Well, now there is an FL, and that's fluorine. People confuse magnesium with manganese, calcium, and carbon. So you've got to be really careful what you do. There are more two-letter symbols than one-letter symbols. If that's going to give you anything, the only ones that are really one letter are hydrogen, potassium, vanadium, I'm quickly scanning a table, boron, carbon, nitrogen, oxygen, phosphorus, sulfur, iodine, uranium, and then the rest are all two-letter symbols. So kind of err on the side of two if you're having to make a guess. So let's actually look at this periodic table square and see what it tells us. Okay, first of all, when you look at a square, there's going to be two numbers generally with it. The one that is just a single digit. Here you see just the single number 1, digit 1. That's the atomic number. The one that is a decimal, so there's your atomic number. The one that has a decimal, that's the average atomic mass. If you're confused on how to do average atomic mass, we made a whole video on how to calculate average atomic mass. It's the percent abundance as a decimal times the mass of each individual isotope. It's in the isotope section under atoms. Okay, so let's look at this next one. This is a two-letter symbol. This is thallium. Its atomic number is 81. My pencils don't want to pencil today. Let's try this one. That's my atomic number. This one here is going to be the average mass. And you'll notice that this version of the square has some other numbers. This is going to be the ion charge, which is very, very closely linked to what we call oxidation number. And the difference between these two numbers, the number is the same. In an ion charge, the positive negative goes after the numeral. An oxidation number, it goes before the numeral. Most science teachers don't really care. They use oxidation and ion charge independently. Other things you might see in a square, I've seen periodic tables that give you the common electron configuration. Hey, that's pretty cool. So let's look at a periodic table because there's so much here from atomic structure. So the biggest thing we need to do is break the periodic table into groups, metals and nonmetals. There is a zigzag line. Let me make my line a little fatter. That goes right here along the edge of the periodic table. That line separates metals, which are on the left, from the nonmetals that are on the right. There are more metals than nonmetals. If you get confused, the easiest thing to do is go look and think of something that you know for certain is a metal. Like, let's say the one that's right here, AU. We know gold is a metal. It's on the left, so we know metals are on the left. Something we know is a nonmetal, something like oxygen, it's going to be on the right. Okay, so what happens on the zigzag line? On the zigzag line, we have something called metalloids. Metalloids have properties of both metals and nonmetals. Boron is a metalloid, as is silicon. Oops, let's get this color in. As is, oops, I did that wrong. Let me fix that. I went too far over. These two. As is, it's arsenic. These two. This is antimony and tellurium. And then polonium. These ones down here at the very, very bottom, yes, they should follow that trend, but I'm going to do these. We know that At is a nonmetal. It's a halogen. I'm going to do this one here as a dash line because we're not 100% certain on that one. We have such a small sample, it's really hard to tell when you only get 1 or 2 atoms of something. All right, so metals, what are the properties of metals? They're shiny, they have a luster, they're electrically conductive. They're all solids with the exception of mercury. Nonmetals have solids, liquids, and gases. Metalloids are going to have properties of both. Some nonmetals are also brittle. Some metalloids are brittle but shiny, so it has properties of both metals and nonmetals. The metalloids we're finding are more and more unique uses. Okay. Then when we look at a periodic table, we have to divide it into blocks. And this kind of is like the SPDF blocks. We have main group elements. Our main group elements are going to be your S and your P orbitals. So all of these guys are main group. They're also called representative elements. And your P block. So these guys here are main group elements. Okay, so those are your main group of representative elements. The next thing we have are families, groups, numbers, things like that. Okay, so we're going to go here and we're going to talk about families, groups. The columns are called families or groups. So these things that go up and down. And they're numbered 1 to 18. Now you will see some different characteristics here. Sometimes the representative elements are a number with the letter A. And then your non-representatives, non-rep, are going to be the number and a B. On some tables, they'll start to recount here in the transition metals, the middle part. Okay, so groups or families, things are grouped by similar properties. Everything in a group is going to have a similar property. And then periods are what run down the side. These are your energy levels. So we have 1, 2, 3, 4, 5, 6, 7 currently. Then we've already finished element 118. Remember these lanthanides and actinides? These guys right here, they fit into this spot right here. So our next one that's going to come up is going to be starting in group 8. So periods run across, and going across, they're going to change in a regular, predictable manner. Why? Because you're adding a proton to that nucleus while the electrons are all still in that same energy level. And that's going to be really important in our next video when we talk about trends. So groups and families all have names, and you need to learn your names. Okay, this group 1A, you can see here they've got the AB designation. This is from 2010 Ton Helmstein's table and about chemistry, give him credit. We have the alkali metals. First thing here. Here, this table has hydrogen as a nonmetal. We can see this sort of mustard yellow color as nonmetals. I like to count hydrogen as an alkali metal. The reason I do that, the core of Jupiter has liquid metallic hydrogen. Yeah, it's electrically conductive, so it belongs in this alkali metal family. Some people pull hydrogen out and make its own square kind of off in the middle because it's just one proton and one electron. Some people don't even classify hydrogen as an element, just two subatomic particles. But either way, this first family that's here in bright pink is the alkali metals. They're soft, silvery white, very reactive with oxygen, very reactive with water. They'll actually produce a flame. The hydrogen gas released from water will ignite. The term alkali comes from the fact that when you add it to water, it's going to make an alkaline or basic solution, acid base. It'll be a basic solution. The family next to it is similar. It's still silvery white. It's a little harder. It's a little more brittle. It's just calmer than the alkali metals. One thing to keep in note, as you move down the family, they get more and more reactive in the metals. So francium is our most reactive metal on the entire periodic table. It is more reactive than cesium. Cesium is more reactive than rubidium. There's a really cool Brainiacs video. It's totally not correct, but it gives you the idea of how these things work. Look it up. It's kind of funny. Okay, that next family that's in this medium blue, that's the alkaline earth metals. They also form basic solutions in water, hence the term alkaline, and these are things that are found in rocks. Now remember, things in a family have very similar chemical and physical properties. So when you look here at calcium and strontium, well, strontium has radioactive isotopes. You might remember that from our nuclear set discussion. Our body will take in strontium and use it like our body would use calcium. They're very reactively similar. So that's a dangerous situation. Okay, this middle section right here, these are our transition metals. See the key right here? They are also called our builder metals. Okay, then moving all the way to the far side, the noble gases. Well, they're called the noble gases for a reason. They don't react. Those are also called the inert gases. Next to them in that green color here, right here, these are called the halogens. Halogens means salt formers. So like sodium chloride is a salt. Potassium fluoride is a salt. Salt's really a technical term for an ionic compound, but whatever. Okay, there's some other things you'll see on here. Oxygen is also given a family name. It's called the chalcogens. So that's the oxygen family. And then these other ones, carbon, nitrogen, boron, they could be called the boron family, carbon family, nitrogen family. They're generally just left out because these have so many different properties. Some of them are solids, liquids, gases. They just aren't really, they're a confusing fit. And then of course, down here at the bottom, we have our lanthanides and actinide series. So just to remember, as you move across the table, they increase in mass because you're increasing a proton and some neutrons usually as you move across the squares. So they're going to change in a regular, predictable fashion. Think about those electron configurations and how the electron configuration changes. The periodic table, we see our orbitals right there. So make sure you go back and review that quantum video. Once again, thank you for joining us on Elements of Chemistry tutorials. Stay safe, be kind, Have a wonderful day and a great tomorrow.